Good morning, guys. How's everyone doing? We are the SLAM team. I'm Matt Malencia. Presenting with me is going to be Spiros and Oliver. And shout out to the implementation team over there. Hey guys. So if you have questions on the piece, there's one to go to. So today we're going to be talking about SLAM, and I'm going to give you an intuition of what SLAM is and what the SLAM process is. We're going to talk about common filtering, which is a form of estimation you guys may have heard of, but might not know as well as most engineers should, in my opinion. And then the last two things are going to be an example of SLAM in underwater exploration, because that's kind of the theme of this class, and then visual SLAM. So to get started, I'm going to talk about SLAM intuition by breaking it down into localization and mapping individually, and then putting them together. So the first thing I have is a question for you guys, and that is how you know where you are. And so the example that I want you guys to think about is, imagine you were blindfolded and taken into downtown Boston, and then unblindfolded. What would you do to figure out where you are? Just yell out anything. What would you do? GPS. GPS, great. So pull out your phone. And so how does that help you? How does that tell you where you are?
It has a map.
Great. It has a map, and it tells you where you are on that map. Okay, great. Well, when you were blindfolded, you lost your phone. So now what? What else can you do to figure out where you are?
Landmarks.
Look for the Peru, great.
Landmarks.
Landmarks, yeah, great. So we actually do this a lot as human beings. We have a mental map, and we can use landmarks like the Prudential Building to figure out where we are. Now, I want to talk about one other way that people don't really think about to determine where they are with another scenario. Think about your house or your apartment. You can imagine, again, your mental map of that place. Pick 2 points in 2 different rooms. Imagine walking from one to another. Now, imagine taking that same path with your eyes closed. Show of hands, who thinks they would run into something? Yeah, lots of people. Who thinks they wouldn't run into something? Yeah? Great. I want you to try that out tonight. Come back next week and let me know how that goes for you, okay? But this is the idea that we internally know what we're doing. I can walk with my eyes closed here, and I know I'm not going to run into anything. But as this gets, as you do this more, you have more uncertainty. So, main 3 ways that we know where we are. Internally, we can feel where we're going. We can use GPS, and you were spot on with the Prudential Building. Now the question is, how do robots localize themselves? How do they figure out where they are? And the answer is they actually do it in a very similar way. So the idea of using internal measurements and internal feeling is called dead reckoning. They use things like IMUs. A robot can also use GPS, but GPS isn't always accurate enough, and there's often times when it's just not available. So they actually resort to a map and landmarks just like we do. So the Amazon robots here have a known map of the warehouse that they're in, and known landmarks, which are just features in that environment that are marked by AR tags, QR codes, or RFID tags. So we can reference those to figure out where it is. So let's see a quick process of how a robot might actually do this. Let's say the robot starts with a map. A map can be represented by some landmarks in the space. And the robot starts in this space at some location that is a bit uncertain, so we're going to represent it by this circle. Now, when the robot moves in this space, the uncertainty of where it is increases. This is like the dead reckoning. So I can walk from here to here with my eyes closed, but I'm guessing when you try in your house and going through rooms, that air is going to compound and you're going to run into something. Please don't hurt yourself. So if we kept doing this, this circle would grow and grow and grow. So instead, we observe the environment and find these landmarks. So here are some observations of the landmarks. They don't quite match up because we're not really sure where we were, so where the landmarks are relative. But then we can use those and associate them to our map. And so when we associate to our map, we improve our estimate of where we are. That's the general idea of how this is done. And so the question is, how do we actually do this? And the answer is a Bayesian filter. Now we heard about Bayesian filters 2 weeks before, so before spring break. Anyone remember talking about Bayesian filters? A few people, great, the professor does, that's it. So I'm going to walk through what Bayesian filters are so that you know kind of how they work, because they're very integral to SLAM. So Bayesian filters have 2 main steps: prediction and update. The prediction is using your previous estimate and a mathematical model to make an estimate or a prediction of where you are. And then we're going to make an observation to update our estimate of where we are. So let's see it in action. We start with the robot in one-dimensional space. And there's some probability distribution of where it is. This probability distribution can be any probability distribution. Square, triangular, Gaussian, whatever. It can be anything. The robot is going to move. The mathematical model is going to be used to make a prediction of where the robot is. Observations are going to be made. We now have two different probability distributions, and then we're going to combine them into a new estimate. Then, that estimate is used as our seed, and the process is repeated. The robot moves, and the same process happens. Sorry about this, robot just popping. So this iterative process is able to use both the model and observations to create better estimates of where the robot is. So let's see this in a flowchart. We're going to be building this flowchart up. So anytime you have questions about this flowchart, please ask. So if we're observing our state directly, the flowchart and Bayesian process for localization is quite simple. We make a prediction of our position, because that's what localization is worried about, and then we use observations of that state to update. One sensor that uses observation of the state directly is a GPS. But as we said, GPS isn't always available, so we have to resort to our map and finding landmarks. So we have to expand this just a little bit, where we observe our environment, and then we have to do a little bit of work to get it in a form that we can work with. We extract the landmarks from our observations, and we associate them to the map to figure out where we are. So, any questions on localization and using a Bayesian filter to do localization? Great. So our next step is mapping. Now mapping is building a map from scratch. Specifically, we can view it as putting landmarks in space to build this map. So my question to you guys is, how do you guys think mapping is different from localization? Any thoughts? Yeah?
So mapping constructing a map, whereas localization is finding yourself within the map?
Yes, good. Any differences in how that is done that you can think of?
So I guess mapping would be finding defining a landmark, and then localization would be putting yourself in context.
Great. When we were doing localization, we used a known map to figure out what our position was. When we do mapping, we use a known position to figure out what our map is. So, let's see an example. Now we have a robot in the same space, but he now knows where he is, but he doesn't know what anything is around him. He'll make some observations that are noisy, because all observations are, and he'll decide to add some landmarks to his map. So he started building his map. He moves in this space, and he knows where he's at, and he makes some more observations. As we see, some observations overlap with the map that he's already building. In this case, he's going to update those landmarks. So, using both the previous map and the new observations, we can update it, and then with new observations, we can add it to the map. And then the last thing that happens in mapping is sometimes we actually remove features. So if you imagine we put something on the map, and then later we're not observing it anymore, we can take it off. This is the idea of map maintenance. So, starting with the localization flowchart here, to get to mapping, instead of predicting and updating the state of the robot, we're just predicting and updating the state of the landmarks. And then as we said, we have to add in a little more to do map maintenance. So here are predictions and updates of the landmarks of our map, and some map maintenance adding to that. So within mapping, one thing that's really important is the idea of loop closure. Loop closure is being able to figure out that you're in a place that you have already been in. So in order to do that, this is integral in the map association process. So we want landmarks that we can detect and that are unique. So in this example, if we drive from A, past C, past B, and around, we put B on the map, and then when we see B again, we want to identify that that is the same feature or same landmark as we saw before, because if not, we add it as a new landmark to our map. Instead of saying, oh, it's already on my map, I can actually tie this whole map together into one cohesive picture. So, any questions on mapping? Great. So now, we're going to put the two together. We do have a quick question.
Right?
Yeah.
Okay, so the terminology has always been closure, right? But is it really about loop closure? So it is the case that in the process of mapping, you always need to decide is something a new feature or is it something that you've already seen, right? And that's the fundamental question that it's asking, that the algorithm is asking at every step. Is it a new feature or is it an existing feature?
Yes.
And deciding which of those to make it. And that phenomena occurs when hallways come around, but loops are just one instance of it.
Yes.
Is that right?
Correct.
And the algorithms don't really care that it's a loop.
No, it doesn't.
Okay.
Yeah, thank you. So now we're going to put localization and mapping together. So my question to you is, first, we need to localize and map when we don't have ability to know our position. One example of this is being in an area that is GPS limited. And then two, when we don't already have an existing map. So my question is, can you guys think of some scenarios where both of these things hold true? Yeah.
You're walking around the status center?
Great, walking around the status center. More examples. Can we get some examples where robots might be involved? Yeah.
Like if you send a robot to an underwater cave to explore.
Good. Yeah. Kind of what this class is all about, right? Good. Any more? Yeah.
Go and do a different planet.
Go into a different planet. Great. Some great examples here. So underwater, other planets, under ice. Home robots are also a big deal in this because while you can get a map of every home, it's just not tractable. So instead they rely on SLAM to build the map. So we know why SLAM is important because we're going to use it in these unknown environments where GPS isn't available. But why is it difficult? And the answer is, it's a chicken and egg problem. So in order to do the localization, we need the map. In order to do the mapping, we need our position. And so, which came first? Well, what SLAM does is it kind of just works on both at the same time, using the best estimate that it has so far to help the other out, and then just bounce back and forth improving both. So, again, Bayesian filters are integral to SLAM. So in localization, Bayesian filter was updating the state of the robot. In mapping, the Bayesian filter was updating the state of the landmarks of our map. So in SLAM, we're just going to use one Bayesian filter and put both states, the state of the robot and the state of the landmarks, in there. So we can actually use the mapping flowchart that we saw, and the only thing we have to do to add localization to it is in this predicted update state, we add the robot state in there as well. So now, do you guys have any questions about SLAM and putting those two things together before I move on to common filtering? Great. So common filtering is an instance, it's a specific subset of Bayesian filtering. So within our SLAM process, there's lots of disciplines. You guys will learn later about some of the computer vision and signal processing that goes into the observation and landmark extraction side, some of the optimization and graph theory that goes into map association. But I'm going to talk about the estimation side of this. So Bayesian filtering, which does estimation, can be done with a common filter, a particle filter, or a grid-based estimator. A common filter has two assumptions. Your system is linear, and your system's noise is Gaussian. Now we love Gaussians because they can be easily represented with just a standard deviation and a mean, which means it's computationally very efficient, but because of these assumptions, it's not always as flexible. Many times we have non-linear systems, so this doesn't quite work for it. Particle filters they sample your distributions and then propagate those forward. So they work in most models and with non-linearities, but they're very computationally expensive. And then your grid-based splits your probability of distributions into a deterministic discrete grid and then propagates those forward. It's kind of doing a little bit of both, not really doing the best of either world, so it's often not used. I'm going to be talking about the common filter. So as I said, the common filter uses Gaussians. As we saw earlier with the Bayesian filter, you take a prediction, an observation, you combine the probability of distributions. When you're using Gaussians, you can just multiply one Gaussian by another, and you get a third Gaussian, your estimate Gaussian. So let's look at how this math works. When you multiply the two, you get a new mu and a new sigma, and we can just do some algebra to pull out this k. This k is called the common gain, this common gain. You can think of it as just a weight between your measurements and your model, and it's describing the confidence in it. So if you imagine you have a perfect sensor, you don't need to really worry about your predictions at all. You're going to be weighted really heavily to the sensor side. So it's just a weight between how these two are combined. So to do common filtering, as with all Bayesian filtering, we have to start with a state. A state is anything that describes the configuration of our system. We're going to use position and velocity. That's a really common thing with robotics. We want to know where we are and how fast we're moving. Now, moving into multiple dimensions, we just move our Gaussian from a mean and standard deviation to a mean vector and a covariance matrix. So this is a representation of the state. Now, first step of common filtering is the prediction step. We're going to take our previous estimate of where we were and transform it into some prediction using a mathematical model. When we're using position and velocity, this can be a kinematics model. Position changes with delta t and velocity stays the same, so we end up with an equation for our new predicted state based on our previous state. And then this is just an update, the prediction of our covariance matrix based on this theorem down there. But this doesn't fully represent our prediction because there's a bit more that goes into it. There can be known inputs, such as the robot controlling itself to go faster or slower, and external uncertainties. So we can add those in, and we get the full prediction Gaussian here. So now we have our first Gaussian, the prediction. It is, as you see, based on the last prediction, or the last estimate, control inputs, and some additional environmental noise. So now we need our second Gaussian, which is from sensor outputs. Sensor outputs are really noisy, so they automatically are represented by a Gaussian. We can get some reading, which is put at our mean, and then we generally know the Gaussian based on the errors of our sensors. One thing to note here is that the sensor space is not the same as the state space, because sensors usually don't tell you this is your velocity, but they tell you something that can transform into what the velocity is. Example of this is with temperature probes. They're actually measuring velocity sometimes. They're not actually measuring temperature. So you have to transform from that, sorry, did I say velocity? They're measuring voltage. So you have to transform from voltage to velocity. So in the same sense, we have a sensor space here, which is different from the state space. So we need to know how to transform back and forth, which can be represented by h, which is just some transformation from the space of your state to the space of your sensors. So we have our two Gaussians. We need to put them together. To do so, they need to be in the same space. So we're going to transform our state space, our predicted state, into the sensor space. Now we have two overlapping Gaussians, and as we saw earlier, we can combine them using the Gaussian multiplication. So this is what we saw earlier with one dimension. To move it into two dimensions, again, we just make everything mean vectors in covariance matrices instead of means and standard deviations. Quite easy. So we have two Gaussians here, our prediction and observation. We have the math we just showed you, and when you plug those into there, you get your estimation. And then you keep repeating this, and you have your entire common filter estimating the state of your system. Now, as I said earlier, common filters can be a little limiting because they assume linearities. So sometimes, well, really often, there are linearities in our system. This equation is the transform between a radar space, a radar sensor space, and Cartesian coordinates. And as you can see, for example, in the middle here, our tangent, very nonlinear, so common filters don't like that. But extended common filters have a way around that, and they just linearize, as with a lot of nonlinear solutions, we just linearize around the mean, and then as long as we're close enough to that, it works well enough. So in this example, we have a Gaussian. We can pass through this arctangent filter, and as we see, our output is very much so not Gaussian. With common filter, we want to maintain that Gaussian throughout. But if we create a linear approximation, we get a Gaussian out. So this doesn't work for things that are very nonlinear, but for a lot of cases, and the cases you'll see later, it works to approximate nonlinearities using things like, usually it uses Jacobians, which are just your derivative. So that is how we deal with nonlinearities, by using an extended common filter instead of just tradition. So that is an overview of what SLAM is, what a Bayesian filter is, and specifically what common filtering is, and how it's used to predict and update both the state of landmarks and the state of your robot. Do we have any questions on the general intuition of
Can I
SLAM?
go back one slide?
Yeah, absolutely.
So here you have the tangent of x equals 0.
Yes.
There's any cases where you don't have x equals 0 and you need to linearize another point?
Yeah, so wherever your state is, whatever your mean value is, you can linearize around that, and that's what the Jacobian does. So this linearization could really exist on any part of that curve. And again, as long as you're close to that linearization, it tends to be pretty accurate.
So you need to update that tangent
Yes,
line.
so one of the
all
things
time.
that's difficult with the extended common filter is you have to do that linearization every time, so it is more computationally expensive. Great insight. Any other questions? Good, so I'm going to pass it off to Spiros to talk about a specific example of using SLAM.
Thank you. Okay, so up to now we have seen what is a general algorithm for performing SLAM, and you have also seen how to implement the Kalman filter, which is one way of dealing with the problem. We're going to talk about a specific example of SLAM in underwater environments. Do you think that just what you have learned you could go and implement this, or are there some specific challenges that we have to deal with in underwater environments? And the answer is yes. So what are some specific challenges in underwater environments that differ from doing SLAM on land, for example? Can you imagine?
In the underwater vehicle, the water is moving, so your location is kind of not certain, because
Exactly.
if the robot is on the ground, you know, like you're not moving, you're not moving. But in the water, you don't know that.
So there is more uncertainty in our position. Other insights? Yeah.
There's not so much like landmarks that can be used.
Very good. Yeah. So we have to deal with environments that are unstructured, and we cannot have landmarks there. So there are a few challenges, and that's why we're going to talk about a few more topics. Namely, we're going to talk about scan matching, how to deal with raw data from the sensors. We're going to see how we can handle sonar imaging data, and I will explain why. And then we're going to see a full example of SLAM for underwater. So, as correctly you said, in these type of environments, they are unknown, but they are also unstructured, which means that there is no prior about what we're going to see, and we don't have a way to really extract landmarks from there. Another problem is the modalities that we can use underwater. So do you think we could be using, for example, a camera? No, a camera will not work, because in deep sea there is low water visibility. The camera will only give us information about things that are close to us. We cannot rely on that. Will the LiDAR work? No. LiDAR will not work either, because water has high absorbance. We will not get the data that we want from there. So what can we use? We can use a sonar. And more precisely, we're going to use a mechanical scanning imaging sonar. So this is a sonar attached on a device that rotates around on specific intervals. This can give us a scan of 360 degrees around us, or a narrower angle. At this specific step, we get one beam of information. The data has some intensity, and we know we get this complete image in the end. So, as you mentioned correctly before, the vehicle will keep moving underwater, and the sonar is slow. So a full scan, like a 360 scan of the environment, may take several seconds. For example, in the paper that I'm based on, it would take up to 14 seconds to complete one whole scan. This means that each of the beams that we're getting and combining is actually sensed from a different place, which in the end results with distortion. So instead of having a scan that will fit our environment, as here, we get this scan that is highly distorted. So that's a problem. And to add to the uncertainty, we have the expansion of the beam, which means that we get data from equidistant points that are on the sphere, because there is some range that we receive here. So this is just another challenge. So setting up our problem, we have an underwater autonomous vehicle. It is equipped with the mechanical scanning imaging sonar. And for dead reckoning, we have a Doppler velocity logger that gives us the velocity, and the motion reference units that will give us the headings. Let's see how we can do the SLAM now with what we have.
Wait, can you go back a slide? Can you see, just say a little bit more about what differentiates those? So what is a motion reference unit?
So this unit can give us the headings at each point, so we know how much we have turned, what is the angle. And the Doppler velocity logger will just give us the velocity, how fast we're going. So combine these will give us a whole pose through the reckoning. So going back to the SLAM diagram that we saw before, we are changing our observation. Now we're using the NSIS. And let's see, we will try to move on to the diagram and do landmark extraction, but we said no landmarks. So, okay, no landmarks, we're going to do scan matching. Scan matching is the problem of obtaining an estimation of the displacement given a reference scan and a new scan. For example, here we have like a robot in two different poses. From here it is getting a scan, that's these yellow points, with these lines, and from here it's getting the same scan, but from a different pose. So now, having this, we need to estimate what is the transformation that gives us the new position of the robot. And the most fundamental algorithm that helps us to do this is the iterative closest point. So we have 2 point clouds. The blue and the yellow are the two scans from different poses. First, we try to compute for each point of the first scan, we try to compute the closest point of the second scan. So this creates correspondences between points. After we have this, we try to align all the matching points, and we estimate transformation that gives us the best matching. We apply transformation to the source point cloud. Now, the result will not be perfect, so we have to iterate, and we do the same. We find again the closest points, we obtain the transformation, and we apply, and we keep doing this loop until we converge. Is it clear? Okay. Now, it turns out that this works pretty well for some cases, but there are cases that it will not work that well. And one such case is when the two scans are obtained with poses with very different angles. Now, what is this going to do? Points that are far away from our sensor will end up having a very long distance between them. And in that case, just computing the Euclidean distance between the points might give us wrong correspondences. This is why another approach has been suggested. So instead of using the Euclidean distance for calculating the closest points, we use a metric-based distance, which is taking into account this rotation, so it is expanding on some range. So here you see like what are equidistant points using the Euclidean distance, and these are equidistant points from this using the metric-based distance. So this turns out it can work pretty well for scans that are obtained from very different angles, but still it cannot deal with uncertainty. And so when we have noisy data, when there's uncertainty in the data, this will also fail. So uncertainty means probability. So there is this approach, probabilistic iterative correspondence, that instead of finding the one pair of matching points, like instead of finding a one-to-one correspondence, it builds a probability of corresponding points. And turns out that this approach works a lot better for noisy data. So for comparison here, we have scans obtaining the purely biodometry data. And here you see how using the previous method that takes into account the angles aligns them, which is pretty good. But we can do much better with a probabilistic approach. So you see here, for example, these alignments have worked much better in that case. Okay, so we can do the scan matching now. Yeah.
I'm sorry, what did you add there to get the probabilistic model? What was the intuition behind the probabilistic model?
So when we have noisy data, the previous approaches would not work that well. So here we find like a probability that reflects the certainty of how well the data are matching. Okay, so we have our scan matching now, and maybe we could just apply our SLAM as it is here, but not yet. We said there is a lot of distortion in the original data. So we need to do something to remove this distortion. And so, as a reminder, each of these beams is obtained from a different position. So the intuition here is that if I knew the position from which each beam was obtained, I could apply the correct transformation to get my correct image. So in the observation, we need to do a pose estimate for each beam that gives us the full scan. We fix the distortion, and then we should be able to continue. So more visually here, you can see if this is my complete scan, and the robot is moving while taking the scan. Each point has been obtained from a different location, and we're going to calculate one central location and the transformation that I should apply to each of these points so that it is referenced from this central location. Let's see how this would work. First step is to do a beam segmentation, so you know that from the sonar scanning we're getting this complete 2D image with data on each distance, each point, on points of different distances. So actually I want to find what are the edges here. I can use a simple threshold approach to get the actual boundaries. So I transform like this image to edges. And then we can model the movement of the robot using a constant velocity model with some acceleration noise. In addition, we obtain data from our dead reckoning sensor. So we get the velocity and we get the headings at this position. And now that we have the model and the data, what we will learn that we can do here, we can use an extended Kalman filter to get a better estimate of our position on each point. So we get a better estimate from the position, so now we know what the transformation should apply, and we can do the scan forming. We have the scan forming, we get the next scan forming, and then we can register the two scans using the PIC algorithm, the probabilistic isotope correspondent that we saw before. Turns out if I just keep doing that, so for each pair of scans, I use the PIC, I keep moving, I can actually obtain a full scan of my environment and keep track of my position. So here is what this would look like. This is an example of an underwater robot navigating inside this marine environment. This is what we would get by pure odometry. So the blue points show you what the robot thinks that the boundaries are. The cyan line shows what the robot thinks that its path was, and the yellow line shows what the actual path was through the GPS. And you see that by applying this algorithm itself, we get much better results. So the results are much better, but there's still quite some deviation, and we did not use the whole algorithm that Matt talked about in the form that we saw before. So if we actually go here and we combine the two things together, we can get a better estimate. So this is the augmented state, the extended Kalman filter slump. And the difference is that once we have this part done, we are going to use one extra Kalman filter that will keep track of the global positions of the robot at each point. So how would this work? We start with our robot in the environment. We initialize our map by using the approach that we talked about before, and we continue getting the next scan. So we can update our estimation for the new position based on the dead reckoning. So we get a new estimate from there. At the same time, we're trying to do the loop closure. So we have the scan of the first pose, we have the scan from the second pose. We see how well these two scans match. If there is enough overlap between the two scans, then it means we have a loop closure, and we register these scans and we update our extended Kalman filter. So here, there is, like, we keep track of a number of states, and we compare for loop closure inside this range, so the last few states. We don't just check the one last state. So we have the two scans, right? We get the transformation by the PIC algorithm. And now that we have the transformation from this PIC, we can feed it into the extended Kalman filter and get our better estimate of the new position. So it turns out this approach that is using both corrections for the local position and for the global position is giving us a lot better results. So here you see in red, it's the same marine environment as before. In red, the red line is what we get from dead reckoning. The blue line is what we get from